video, we're going to start looking at conformations of acyclic alkanes. And again, if you watch that introduction video that I did at the beginning of this module, I did show some models, and I will pull out some models as part of this video also, but I did show where I had 2 carbon alkanes, so an ethane, and we could spin the bonds, right? Our sigma bonds have free rotation. Remember from our last video that if it's cyclic, it doesn't have free rotation because it's locked in a ring. But if I just have a straight chain alkane, there's no barrier to that rotation. Alkenes do not have free rotation around that double bond because of that pi bond locking it in place. But just a regular alkane that's not in the form of a ring, I do have free rotation. So conformations of acyclic, meaning that it's not cyclic, alkanes. So straight chain alkanes are acyclic. So sigma bonds have free rotation about them. So I can take a sigma bond and rotate it. So there's no barrier to that rotation, right? Remember, we do want to exclude cycloalkanes. Because they're in a ring, I do have a barrier to rotation. But acyclic alkanes, I'm going to have free rotation about that bond. So because of that, I can change the orientation of the various atoms that are bonded to that alkane in space. So because of that, the orientation can change in 3-dimensional space. So in that introduction video, I had my straight chain alkane, I had the 2 green atoms, and we could rotate it where sometimes the 2 green atoms were on the same side of the molecule, sometimes they were on different sides of the molecule. And all of those orientations in between, it doesn't just magically go from the top where they're on the same to being the opposite. It goes through all of the spots in between. So a conformation, that word, these are different arrangements of atoms that are interconverted by rotation around a single bond. So different arrangements of atoms that result from rotation about a single bond. That single bond, remember, is a sigma bond. So if I was to draw just my 2 carbons, I'm going to put a bromine on here just so we can look at something different. And then that's supposed to be a wedge, right? These carbons are sp3 hybridized, so they're tetrahedral. So I do have my 2 hydrogens on each of those carbons also. And that bond between the 2 carbons, and all of the bonds can actually rotate. There's nothing special about this bond. This just happens to be my one between the 2 carbons that we're focusing on. But I can rotate that bond so that bond can twist. So I can go from that structure to any other structure as long as that bond is rotating, right? So if I wanted to compare that one, I'm going to keep the carbon on the left stationary. So this one, I'm not showing it rotating. And then I'm going to rotate the one on the left, and I'm going to rotate it a full 180 degrees. So my bromine is now coming out. And it looks, bond angles are a little messy, but it looks like that. So the relationship between these two, I would say these are different conformations of each other. A conformer is actually a word. So these are conformers. right? They are different conformations. Right, we got the first one changed into the second one by rotating that bond, right? We didn't have to remove atoms and attach them someplace different. I simply had to rotate that bond. So we interconverted them by rotating the bond. All I have is sigma bonds in this one, but just to really drive home, we want to remember sigma bonds versus pi bonds. So we switched one into the other by rotating about that bond. So that makes them conformations, conformers if you want to. It's kind of a weird word to say, but they are conformers. I have heard the word conformational isomers or something like that. I don't use it, which is why I'm not remembering it. I think I've heard it in a lab before. I've never taught this word, and it wasn't actually until I moved here that I heard it called this. It's just if you come across it, I want you to know that it's the same thing. You may have a lab instructor that uses it. It's conformational isomers or something along those lines. I don't use that word. The reason I don't is because isomers is confusing. These are not isomers. Isomers are things that have different structures. These don't, right? All I have to do is rotate a bond. Isomers are things where you actually would have to detach, break a bond, move something to a different spot for it to happen. So even like with our cis-trans, those are isomers. They're stereoisomers, but the only way I can go from cis to trans is to remove a bond and move it to a different spot. So I don't like to call these isomers. If you see this term, I don't want to use it. I'm not going to use it. I would recommend that you don't. If you have an instructor though that is using it, you need to do what they're saying, but just do know that they are not isomers. So I call them conformations or conformers. I'm not going to use the word isomer because, again, they're not isomers. Just be careful. Not actually isomers. I suppose by putting the word conformational in front of it, then it implies that they're conformations, but let's just call them conformations instead. So again, if you see that term, they're what we're talking about. I think isomer is misleading, so I don't like to use it that way. So our two structures, right? They're actually the same thing if we were to name them. They're both 1,2-dibromoethane. They're not stereoisomers of each other because all I have to do is rotate the bond to get one into the other, right? They have free rotation, so they are conformations. So ways to represent different conformations. So representations, right? We have to have a good way to draw them. So there's two main ways to draw them. One, I don't use that much, but it's a Sawhorse projection. And then the second one is going to be a Newman projection, and that's what we're going to use mostly. But I do want to show you our Sawhorse projection first. So I'm just going to use that one with the bromines on again. So, right, I can have the bromines. Oop, there's a hydrogen on that one bond, we missed it, right? I can draw that one, or again, we can rotate that bond and we can get any other version, right? I could have the bromines on the same side, I could have like a 90-degree angle between them, whatever it happens to be. So we have free rotation. So what I'm gonna do when I draw a Sawhorse is we're gonna focus on this carbon-carbon bond. And usually we draw it kind of slightly at an angle. The angle that's going down a little bit is coming out at us. The angle that's going back is going back. The one that's going up, sorry, is going back. And you can do it this way, that's fine. Now this is the one that's coming forward, and this is the one that's coming back. It doesn't matter which angle you draw it at. You're just gonna draw it at a little bit angle. So that is the bond between those two carbons. The way that I have this one drawn, I'm gonna try to replicate this in a Sawhorse. This carbon here I'm gonna use as my front carbon. You can pick either one, but that bromine is going up. And then I'm going to draw those two hydrogens. If I look at that back carbon, that bromine is going down, and then those two hydrogens. So that would be its Sawhorse projection. If I wanted to draw the one where I had the two bromines, and this is the one that kind of where the name comes from, because it looks more like a sawhorse. So again, I'm going to draw the angle, and then I'm just going to draw the hydrogens first so you can kind of see where the name's coming from. It's supposed to kind of look like a little sawhorse, right? These are the legs. I'll fix it. And then this is the thing on top where you put your piece of wood or whatever it is you're working on. So angle it. Those are my two hydrogen. Bromine going up, bromine going up, and my two hydrogen. So these different conformations do have names. Not every version has names, but the two where I have my two bromines on the same side, and it doesn't have to be bromine. I could do all hydrogen and I still have these names, but where the bonds are lined up. Let's actually change them. Sorry, you can keep your notes bromine if you want. You don't have to change it, but I'm going to change it to hydrogens because I don't want you to think that it has to be different. They could all be hydrogens and these names still apply. What we're noticing here is that this bond, this sigma bond, is lined up directly with that sigma bond, right? If I was to look down the end of this, those bonds would be directly one right in front of each other. This bond here and this bond here are directly lined up with each other, and then same with the other two that I haven't highlighted. So this is called an eclipsed conformation. It's eclipsed because those two bonds are eclipsing, I guess the three sets of two bonds, if that makes sense, are all eclipsing each other. They're lined up, right? This bond here that I'm making thick is eclipsed with that one. This bond here is lined up with that one, they're eclipsed, and that's eclipsed. So this would be an eclipsed conformation. This first one is staggered. Because they're staggered, right? This, if you were to look on the end, is right between those two. And then this one, again, if you look down the end, is right between those two. So that would be my staggered conformation. Our other way to draw it is a Newman projection. And after I show you this one, I'll actually put the video up and show you some models. And we'll look at both of them. So a Newman projection. And this is the one I use most often. It's a little weird to kind of look at first. But what we're going to do is, again, we're going to look at our model. And let's do our staggered first. I'm just going to stick with hydrogens for right now. And we're going to make one of these hydrogens our front. So essentially we're going to take this and we're going to turn it 90 degrees. So we're looking straight down this direction. So we're sighting down the carbon-carbon bond is kind of how you would say that. And the carbon in the front we're going to represent as a dot. And the carbon in the back we're going to represent as a circle. And honestly, it doesn't really matter which one's the front and the back. You're just going to have one of those carbons when you're sighting down that carbon-carbon bond be a dot and the other be a circle. And then the ones that are attached to my front carbon, so I'm looking at this carbon right here. I have that hydrogen going straight up. That's supposed to be a hydrogen on an arrow. And then I have these two hydrogens. And then because I did staggered, my carbon in the back, this pink one, on it, and I'm attaching it to the outside of this circle. If I was to do, I'm going to do it wrong, so be careful. Don't copy this down unless you want to copy it down wrong. Don't do that, because now I gave that front carbon 5 bonds, right? I'm attaching it to that back carbon. So this bond needs to end right where that circle is. And it's staggered, so they are alternating. So this would be my staggered conformation in Newman. Eclipsed. So we can't draw it truly eclipsed. If we were to draw it perfectly eclipsed, you would actually not see the back bonds and atoms because they would be lined up directly in front of the front one. So what we have to do is we have to just draw them off a little bit. So this is going to be my back hydrogens. So they are actually really eclipsed, but again, we can't really see it if we draw it that way, so you just draw them off a little bit. So eclipsed and staggered. So we'll look at some models here, and I can put them in both the Newman and the Sawhorse projections. So our model, I have an ethane molecule here, right? And I just have that single bond, so we can freely rotate it. So different conformations. Every time this moves a little bit, it's a conformation of the one before it moved. So looking down the end, so kind of a Newman standpoint, if I wanted my eclipsed version, I would have these guys lined up completely with each other, right? If I get it perfectly straight, you can't see the ones in the back because they're eclipsed. So when we do that projection, we actually drew it just off a little bit, whether you go that way or this way. But these bonds, right, this atom is completely being eclipsed by those. So they're lined up directly. I can rotate this, and when I rotate it 60 degrees, I end up with one of my staggered conformations. So it's alternating, right? This, then this. So looking again down the end, looking at my Newman projection, I'm gonna hold it so my hand's not everywhere. We end up with our staggered conformation. The Sawhorse version is just tilted a little bit. So if I go back to my eclipsed, if we just kind of angle it a little bit, it's my Sawhorse. Again, I don't use those very much, but again, eclipsed, that's the important part. Staggered. Conformations, staggered and eclipsed, are not equal in terms of stability. One is actually favored over the others. So there is an energy cost as it rotates. It's still rotating, but our molecule is higher in energy in one of those conformations than it is in the other. And if you had to guess, just based on what you know or gut instinct, which of those two conformations would you like better? Yeah, most people usually pick this staggered, right? Instead of stuff just lined up in each other. It's easier if you didn't get that, that's okay, because I haven't explained why yet. But the reason for that is, remember, those lines are electrons, right? I don't have lines with little H's on them and C's, right? I have orbitals with negative charge in it overlapping. So looking at, I'm just going to focus on this one here for my picture. The electrons that are in this bond are lined up directly with those electrons. And what do like charges do? Yeah, they repel. So those actually want to repel a little bit. And then these are lined up with those, and those are lined up with those. And it's not super happy. If we can stagger it, where these electrons in my other structure are between those two sets of electrons, right, those bonds, then it's going to be lower in energy. So there is an energy cost, right? It has free rotation, but it's not equally stable in all of those conformations. So in general, our eclipsed conformation tends to be higher in energy than the staggered conformation. And our reason for that is we have what's called torsional strain. And that was those electron repulsions. So torsional strain is the strain felt between bonds that are eclipsed. So it's an increase in energy due to eclipsing bonds. It doesn't matter what's bonded to them, it's actually the electrons in the bond. We're going to have another type of strain in a little bit that is going to matter what's attached to it. But here, it doesn't matter if it's hydrogen or bromine or a big old tert-butyl group. As long as you have one sigma bond eclipsing another sigma bond, you're going to have torsional strain. So an increase in energy due to eclipsing bonds. right? The electrons in the two sigma bonds repel each other when lined up. By lined up, I mean when they're eclipsing. That sigma kind of looks like a delta in the two sigma bonds. So torsional strain, right? Anytime you have bonds eclipsing each other, we're going to have torsional strain. We're going to go through it using butane. What I'm going to do is we'll draw just butane in general, so 4 carbons. And then we're going to draw 4 different conformations, and we're going to rank them in order of energy. So, and we're going to do it in a Newman projection. So our directions, we're going to draw 4 different conformations of butane in a Newman projection, and we're going to then rank them in order of increasing energy. So what I'm going to choose is let's actually draw it a little bit bigger so you can see what I'm doing here. I'm going to choose these 2 carbons in the middle here to be the carbons that we're going to sight down. So we're going to focus on these. So when I draw my Newman projection, one of those is going to be my dot, one is going to be my circle. And then attached to those, right, on those 2 carbons that I have arrows at that I'm about to erase because they're in my way, I do have 2 hydrogens. And then I also, this is a CH3 group, right? I have a CH3 group. So when I draw these in those Newman projections, one of my carbons is going to have 2 hydrogens in that methyl group. My other hydrogen is also going to, my other carbon is also going to have the 2 hydrogen in a methyl group. It doesn't matter which one you start with. I'm going to start with a staggered version. It also doesn't matter. Let's do this real quick. I shouldn't say always. I often do it this way where my front carbon, right, this one in the front, I have like going up. If you wanted to do it this way, that's perfectly fine also. It doesn't matter. Different instructors tend to like do it differently, just kind of whatever our habit is. Honestly, I would have to look in the book to see which way they do it. So as long as you're making it staggered, you can make it upside down from how I'm doing it. So back to this, my front carbon. And then on that, I'm going to put a CH3 group and 2 hydrogens. It doesn't matter which of those spots the CH3 group goes in. It doesn't matter which of those spots the hydrogen goes in. It only matters that attached to that carbon, I have 2 hydrogens and a CH3. My back carbon, like I said, I'm going to start with staggered. You don't have to, but that's how I'm going to start. My back carbon also has, right, 2 hydrogens and a CH3 group. And I'm going to put my CH3 groups opposite of each other. You don't have to. What you do have to do, though, is make sure that line goes to the carbon and not the hydrogens. That's a really common mistake. I'm going to draw it wrong, and I will mark off for it. Really common thing that people do is they do this. Now you just gave hydrogen 2 bonds. You can't do that, right? Hydrogen can only ever have 1 bond. That carbon, right, this carbon right here I just made a big dot on, is bonded to carbon. So please make sure that you bond it to the right atom. So CH3. I know it's kind of awkward to draw it, but it does need to be attached to carbon, not hydrogen. So this is one of my conformations. So what I'm going to do, because I like to be systematic about it so I don't miss anything, is I'm going to rotate the back carbon. You can rotate the front carbon if you want, but I'm going to take the back carbon and I'm going to rotate it clockwise 60 degrees. So essentially I'm going to take this group and it's going to come over here and eclipse this. This hydrogen is going to come over and eclipse that. This is going to come down and eclipse that. So we're going to take the whole back carbon, we're going to rotate it those 60 degrees. And I want to erase this so we can look at it nice and clean when we're done. So again, I'm keeping the front one the same. You don't have to. You can rotate the front and keep the back the same. So I'm horrible at drawing circles. Anyway, it's not getting any better. So again, I'm keeping the front one the same. So I'm just going to put those groups on there. Make sure you bond it to the carbon and not the hydrogens. And now I have an eclipsed one. So this methyl group came over here, again bonded to the carbon, hydrogens over here, and then hydrogens over there. And then I'm going to do the same thing. I'm going to take this one, I'm going to rotate the back carbon another 60 degrees. So this group is going to come over here, this is going to come over here, and this is going to come over here, and we're going to have another staggered conformation. So again, I kept the front the same. And then I rotated the back. Sorry, so it's eclipsed. I might have, sorry, it's staggered, not eclipsed. I might have said it backwards, right? It was eclipsed. The one I'm currently drawing is staggered. So that hydrogen that I just put on there was that hydrogen. It moved over. This hydrogen is now this hydrogen, and this methyl group is now this methyl group. Again, make sure you attach it to carbon. You don't have to, write it backwards. You just have to make sure that that line goes to carbon, right? If you like that better, by all means, do it that way. Just make sure it goes to carbon. So one more rotation, same thing. I'm going to keep the front one the same. I'm going to take the back carbon and I'm going to rotate it clockwise 60 degrees. My molecules keep getting larger. So my hydrogens, my methyl group, and now I have another eclipsed one. This time my two methyl groups are eclipsing each other. And then I have the hydrogens. So we'll come out and I'll make a model of this one and show you, and then we'll rank them according to stability again. Okay, so I did leave off some of the hydrogens just because it gets messy, but this would be my butane molecule, kind of the zigzag way we normally draw it, right? Because it's all tetrahedral. And I have the hydrogens on the carbons that we're focusing on. So when I draw in a Newman projection, the first one that I drew kind of looks like this. Gotta figure out where to put my hands so you can see stuff. But I have the front carbon, I have my methyl group up and my two hydrogen. And then on my back carbon, I have that methyl group, right, in Newman, and those two hydrogen. And then what I was doing is we're taking the front one, we're keeping it the same, and then we're rotating the back. So when I rotate it 60 degrees, we end up with something that's eclipsed. My methyl groups are still off from each other, right? They're not lined up. We rotated it another 60 degrees, we end up with another staggered. We end up with another eclipsed where I have those two methyl groups lined up. If I was to put the hydrogens, I don't have hydrogens for all of them, I just brought two, but there would be 3 hydrogens on each. You can see how close those methyl groups are getting to each other. If you were to actually measure these angles, it actually is expanded a little bit in this version. These angles get bigger because these guys get in the way, right? And again, these are electrons. I have an electron cloud here, and I have an electron cloud here, and they're just totally in each other's personal space, right? He's like, get out of my way. They don't like that. So when we go to rank them, just no, right? We just don't like this one. All these electrons and all these electrons are just too close to each other. They want some room and they don't have any, right? We have to actually expand the bond angle a little bit to actually make it fit. So this is going to be called Steric Strain. I will write that down here in a minute. But when I have larger groups that are essentially in each other's personal space is how I think about it, that's going to be a type of strain. So not only does this one have, right, torsional strain where those bonds are eclipsing each other, but they're also going to have steric strain. Again, I will write that down here in a minute, but that's where these groups just get too close to each other. In my other staggered version, right, this staggered version where they were like, the two methyl groups are somewhat close, I still have some of that torsional strain, right? These bonds rotate also, right? These guys are also rotating. So these hydrogen groups, even when I'm staggered, can still get pretty close to each other. So in that staggered version where I had the two methyl groups next to each other, so this one, these guys here and here are still going to experience steric strain, right? Electron groups just getting too close to each other. So back to our example here. We could keep rotating, right? If I was to take this last one that I just did, still keep the front one stationary, and then rotate it 16 more degrees, this is going to come over. This one's going to come over. This one's going to go up. And essentially what I'm going to end up with is kind of a mirror image of this one. So as far as the types of strain that it has, it's going to be the same. And then if I kept rotating another 60 degrees, I'm going to end up with this one again. And then eventually I'm going to be back to this one. So as far as different structures, this is really what we have. We could draw another version of most of them, but I'm going to essentially have the same amount of strain. So steric strain, I talked about that a minute ago, so let's write that down. Steric strain. Actually, I'm going to go down a little bit further because I'm going to leave some space. We're going to write stuff underneath these. We're going to rank it and we're going to talk about why. So I'm going to scroll down just a little bit more. So steric strain is strain felt due to atoms being close, forced too close to each other. So it's an increase in energy due to atoms forced too close to each other. Basically, they're just, remember they're electrons. Electrons repel other electrons. So you just have too much negative charge in one spot. They don't want to be that close. So when they're that close, they're higher in energy. So an increase in energy due to atoms being forced too close to each other. Sometimes instead of saying it has steric strain, we could say it has steric hindrance. We will use that term a fair amount this semester. So basically, it's being hindered for steric reasons, right? Stuff's just too close. We don't like it. We need to kind of spread out that negative charge a little bit. So increase in energy due to atoms being forced too close to each other, right? Remember, electrons, bonds are electrons. Electrons repel other electrons. So the electrons in our bonds and not even in the bonds, like if we had a lone pair, whatever it happens to be, right? All our inner shell electrons, right? We usually only focus on valence electrons, but those are not the only electrons we have going on. So the electrons, let's just leave it at that, not even say the bonds. The electrons repel each other. I think it's so easy to lose focus onto what these things actually are, right? We look at plastic models, or we look at lines, we look at letters, but that's not what it is, right? Remember, we have big puffy electron clouds overlapping and electrons shared in it, right? And even that, it's not dots, right? It's negative charge. So it helps if you just keep your mind on what it actually is. I always have to remind myself that it's not a piece of plastic. So an increase in energy due to atoms being forced too close to each other. These electrons are going to repel. So when we rank these in order of stability or energy, we want the ones with the least amount of strain to be the most stable. So what I usually do is I'll go through and I'll list the type of strain they have. So if it's eclipsing, it has torsional strain. So this one's eclipsing, so it has torsional strain. This one also has eclipsing bonds, so torsional strain. Remember, torsional strain was due to the electrons in those bonds eclipsing each other. So since those are eclipsed conformations, torsional strain. My staggered conformations do not have torsional strain because I do not have eclipsing bonds. This one, my third one over, because this group and this group are pretty close to each other, this does have some steric strain. I showed that in our model. My first one, those groups are so far apart, it essentially has no strain. So basically no strain. Hydrogens are pretty small. Those hydrogens are kind of close to those methyl groups, but there's nothing branching off of it. It's not the carbon of those methyl groups that are too close to the neighboring hydrogen. It's the carbon, the hydrogens that are bonded to those carbons, right? We draw stuff in condensed. It's another way to kind of forget what's actually going on. Those things look like that, right? So even if I looked at, going over to this one, if I was to draw this out, these and that hydrogen get kind of close. Like there's a little bit of strain there. Not a ton, not enough to really count, but remember that when we write it condensed, we're just writing it that way because it's easier, not because it's more accurate. The other thing we have going on are on these eclipsed ones. I do have some steric strain here. I just said here there wasn't that much, but they're staggered. On my torsional ones, there's eclipsed. So there is a little bit of steric strain between those methyl groups and that hydrogen because they're closer to each other than in the staggered conformation. So we could say there's some steric strain. And then if I look at this last one, I have a lot of steric strain. That's the one I showed where I had the two methyl groups and the hydrogens actually would hit each other unless I expanded those bond angles a little bit. So lots, I don't know if that's a proper word, but lots of steric strain. So if we want to rank these in order of, I don't remember how I said it before, let's do increasing energy. So we want the lowest energy one first. This is going to be number 1. This is going to be my lowest energy. Remember, if it's lower in energy, it's more stable. So we could say this is my most stable. Doesn't mean we don't have the other ones. It just means that as I rotate from one to the other, there's an increase in energy. So this is my lowest energy one. Which one's going to come next? What's your instinct? Okay, hopefully you said this one. It just has steric strain. This one has steric strain and some torsional, so number 3. And then this one is pretty dang ugly. Number 4. This is my highest in energy. Right, it's my least stable. Your book actually shows like a potential energy diagram as it rotates. So it's showing like energy on one axis. And then on the x-axis, it's actually showing it's a dihedral angle. That's the angle between here and here. So that's my angle. And if you didn't even want to do angle, you could just call this number 1. Let's not call them numbers because that's confusing with my ranking. Let's give them letters. So A, B, C, and D. So I have A here. I'm just putting them in the order that I had them. I have B, I have C, and I have D. So A was my lower in energy. So I'm down here somewhere. I'm just arbitrarily picking. I'm going up in energy. Number 2 is down a little bit, but higher than, C is down a little bit, but higher than A. And then I'm going back up higher even for D. And then if we were to keep going, remember how he said we could still take that last one and rotate, we would end up with essentially the mirror image of C. We would kind of come back down and then you would just kind of rotate through those again. So essentially what we're showing, the take-home message is here is that I have energy, and then as it rotates, it's going up in energy, and then it's rotating again, going down in energy, and then it rotates again, right, going even higher in energy. And it's constantly doing this, right? We're not at absolute zero. There's no barrier to rotation. So as it rotates through these different conformations, the energy of the molecule changes, right? When it's in my A conformation, it's the lowest in energy. When it's in my D conformation, it's the highest in energy. I do actually have names for these. I'm going to erase this. Sorry if you needed to pause that to copy it down, by all means. But we do have names for these. So my first one here, try to pick a color I haven't used, where I have my two methyl groups opposite of each other. This is called anti-staggered. Because those two groups, the two non-hydrogen groups, are anti to each other. So that would be anti-staggered. I don't have different names for the two eclipsed versions. They're just both eclipsed. One's just has more steric strain than the other. So they're just letter B and letter D are both eclipsed. But number 2, when I have these two methyl groups next to each other, this is called Gauss staggered. So do know those two terms, anti-staggered and Gauss staggered.